If we want to try a slightly more interesting problem, let's say we go to a gym and there's somebody trying to lift a 100 kilogram barbell, and this person can only push with a force of 800 newtons. What happens? So first we draw the free body diagram, and all we care about are the forces on the barbell. We've got mg downward and the applied force, which is 800 newtons upward. So this is going to be a big problem for the lifter because mg is 9.8 meters per second squared times 100 kilograms, which is 980 newtons. This is more than 800 newtons, so this bar is going to fall. If we do the math here, we see that the net force on the barbell is 180 newtons down. Just for comparison, let's imagine that at the same time someone over here is dropping a 5 kilogram weight with no lifting associated with it. The net force on that mass is mg, which is 5 times 9.8, or 49 newtons down. Which one reaches chest level first? Very often people think that the 180 newton force is, since it's larger than the 49 newton force, that the barbell will fall faster. That doesn't happen in experience, because to make the barbell fall as fast as the 5 kilogram weight, you'd have to let go if you were ever stuck under a weight you couldn't lift, which would be a really bad idea. To figure out exactly how fast each one accelerates, we use Newton's second law. We put in the two forces on the barbell, 800 newtons up and 980 down, and we remember that's equal to 100 times AY. This gives us a downward acceleration of negative 1.8 meters per second squared. For the 5 kilogram mass, on the other hand, we go through the same process and we find, unsurprisingly, the downward acceleration is negative 9.8 meters per second squared. So the freely falling mass gains speed much faster. But once we have this number for the barbell's acceleration, we can ask all the kinematic questions you would have seen in Chapter 2. For example, how long will it take for the bar to hit the lifter's chest? How fast will it be going? How fast is it moving after falling 0.5 meters, for example? So for number 1, if we say the bar starts 1 meter above the chest, we use this familiar long kinematic equation, and what changes is our acceleration is now negative 1.8 instead of negative 9.8 meters per second squared. If we solve this for t, we have 0 initial velocity and 1 meter height. We get just a little over 1 second for that. The speed at impact, we can use this, and again, we don't use g, we use 1.8 meters per second squared. We get negative 1.89 meters per second. What's the speed after falling 0.5 meters? We use this kinematic equation, and we get negative 1.34 meters per second. So these Chapter 4 problems, where you find the acceleration of an object due to the external forces on it, you can attach all sorts of kinematic problems from Chapter 2 to the end of any of these, because once you know the acceleration, you can ask all the same questions from Chapter 2.